Hello there, folks. We are going to take a look at some rolling objects today. In this case, we're going to be looking at things that are having both a combination of translational and rotational motion, and we're going to look at how the forces and the torques might vary depending upon what you're looking at. So in this first example, we're going to go ahead and assume that this ball does have a velocity that is moving to the right, so it has a v0. And let's go ahead and mark the forces that exist. We have our force due to gravity. We have the normal force acting from the connection point between the object and the surface. And then because we know that this object is moving to the right and this is a rough surface, we have a frictional force working against the direction of motion. If I were to go ahead and sum the forces in this situation, the forces in the y direction would be, let's go ahead and call downward positive, okay, would be the force of gravity, which would be mg, minus the normal force, and then that would be equal to 0 because there is no upward overall force. The forces in the x direction would just be based on the force of friction, so let's call the rightward direction positive. So that's going to be the negative force of friction is equal to ma. And then for the torques that we would be involving here, the only force that would be creating a torque would be from our force of friction. So we know that the sum of the torques is equal to the moment of inertia times the angular acceleration. And we would find that the radius times the force of friction would be equal to the moment of inertia times the angular acceleration. Then because we know that this is a solid sphere, the moment of inertia is 2/5 mr squared. And we also know that because this object is connected to linear motion or translational motion, that the acceleration is equal to the radius times the angular acceleration. So we can use these two things and plug them in their appropriate formats to make a connection point between the forces and the torques. We'll do the same thing for our circle rolling down the hill. Maybe this one actually starts with an initial velocity of 0. As the force of gravity comes down, remember that now this is moving straight down, so we're going to need to split this into its component parts, where we have our angle theta. This side that is closest to it, or the adjacent, is going to be force of gravity, or mg cosine theta, and the bottom is going to be mg sine theta for the opposite. We also know that we have our normal force acting perpendicular to the surface that should be equivalent to our mg cosine theta, and then, I guess I'm gonna have to move this for now, our force of friction working backwards against the motion of the ball or the sphere. To sum my forces in this case, the sum of my forces in my y direction, let's go ahead and make down the ramp positive. So that's going to be in the y direction, I have my normal force minus the force of gravity perpendicular, which we said was mg cosine theta, and that's equal to 0. Our force in the x direction is going to be mg sine theta, the parallel portion of gravity, minus the force of friction is equal to the mass times the acceleration. If we're considering clockwise to be our negative value, the sum of our torques would be the torque that comes from the force due to friction minus the torque that comes from the force due to gravity in the parallel, and that's going to be equal to the moment of inertia times the angular acceleration. So then this would be the radius times the force due to friction minus the radius times mg sine theta is equal to angular acceleration times moment of inertia. Whew, right out of space. Okay, Now we get to do our actual problem. In our first example for rolling, we're going to take a look at what happens during a billiards game. In this particular example, a billiard ball has mass m, radius r, and a moment of inertia about the center of mass equal to 2/5 mr squared. The ball is struck by a cue stick along a horizontal line through the ball's center of mass so that the ball initially slides with velocity v0 as shown. As the ball moves across the rough billiard table with a coefficient of sliding friction μk, its motion gradually changes from pure translation through rolling with slipping to rolling without slipping. Develop an expression for the linear velocity of the center of the ball as a function of time while it is rolling with slipping. Before we do our first actual step, let's think about what's really going on with this ball. When the ball is first struck, all points of our ball have the same initial velocity of v0 because it's just sliding across the table. However, as the ball begins to rotate, we start to recognize that there are other forces acting on this ball, and we end up with the velocity at the center of mass remains constant. The velocity where it is rolling forward is greater than the initial velocity, and then where it's interacting with the felt itself, the velocity is going to be less than the initial velocity. I also want to think about the forces that are acting on the ball as it shifts from just translation to rolling. We of course know that we have our force of gravity or our weight. We know that there's a normal force interacting between the surface of the table and the ball as it rolls. And then there is a force acting against the motion of the ball as it rolls, that is a force of friction. Now that we've considered the forces, we're ready to actually consider our first part of our question. We want to develop an expression for the linear velocity. So we're talking about velocity at a particular time, in other words, a translational velocity only. Of the center of the ball, which is great because that tells us that this is pretty much consistent whether it's translational or rolling, and then as a function of time. So what we're looking at this point is just the translational part. To start us off with an equation, we're going to use v final equals v initial plus acceleration times time, because that gives us our initial velocity condition, our final velocity condition, and as a function of time. Which means we need to figure out what in the world is going on with the acceleration. And to do that, since we have forces involved with this acceleration, we need to use Newton's second law to sum our forces. Let's do the forces in the y direction first. I'm going to define my directionality as noted here, so positive is up or to the right, which means I'm going to label this as force normal minus force of gravity, and since it's not rising or falling, that's equal to 0, which then tells me that my force normal is equal to my force of gravity, which is also equal to mass times gravity, or the weight. Now I'm going to sum my forces in the x direction. At this point, the only force that I have going in the x direction is the force of friction. So negative force of friction is equal to ma, because we do have an acceleration happening here. From here, I can substitute in my force of friction as mu k times the force normal equals ma, and then I can substitute my normal force as mg into the equation. From here, I can cancel out the mass on both sides, and I find that the acceleration is equal to the negative coefficient of friction times the gravity. And then finally, I can plug it in to the A expression. Then my final working equation, or my M, becomes velocity final equals velocity initial minus mu kinetic times gravity times time. In part B, we want to develop an expression for the angular velocity, omega, of the ball as a function of time while it is rolling with slipping. So at this point, rather than looking at the translational component, we're looking at the rotational component. The rotational component that's equivalent to what we saw before is angular speed final equals angular speed initial plus alpha time. Just like in the last problem where we had to figure out what was going on with acceleration, now we need to figure out what's going on with angular acceleration. And instead of summing our forces, now we need to sum our torques. In this example, the torque is coming from the frictional force, and that's the only force that's acting as a torque. So we know that's going to be equal to moment of inertia times angular acceleration. For our torque, we know that that is R sine theta, force of friction, is going to be equal to I times angular acceleration. We know that the theta is 90 degrees because here's our radius and here's where the force is acting on it. So that's a 90-degree angle, which means that's going to cancel out to 1. For force of friction, we know that friction is mu times the normal force. And we also know from the previous step that force normal is equal to mg in this scenario. We've replaced everything that we can on the left-hand side, so now we're going to come up and look at our moment of inertia for our sphere on the right-hand side. That's going to give us R times mu k times mg is equal to 2/5 mr squared times alpha. And now I can do a little bit of simplifying. My masses are going to cancel out. I have one r on the left and a square on the right, so that's going to cancel out the r on the left side entirely and the square on the right, which leaves me then with mu k times g equals 2/5 r alpha. Then I can rearrange to solve for alpha. Alpha becomes mu times g divided by r, and then I'll take the reciprocal of my 2/5, so that becomes 5/2. Last but not least, I can simplify and plug in. The first thing I'm going to do is recognize that I have no initial angular velocity because it was not rolling, and then I'm going to plug in my alpha. My final angular velocity is going to be equal to 5/2 mu g over r and then times t. So overall 5/2 mu gt over r. In our last step, we want to determine the time at which the ball begins to roll without slipping, which means we have both translational motion and rotational motion. If we consider again what's going on with the velocities of these two objects when you have both translational and rotational, if we consider what's going on at our 3 points, we know that the velocity at the center of mass is going to be constant. The velocity at the top as it turns the top of the circle is going to be greater, and the velocity at the bottom is going to be 0. So we're looking at the center of mass where we have translation and rotation going on and they can be connected. In other words, we're looking at the place where velocity translational is equal to the velocity rotational. We know that we have an equation for the translational velocity that connects to angular velocity as r times angular velocity. From step 1, we know that the velocity at the time period that we're looking at is going to be equal to the initial velocity minus mu k gt. And then we can set the two equations equal to one another. R times the angular velocity is equal to the initial velocity minus mu gt, and we can plug in what we calculated for the angular velocity here in for mu. So that gives us R times 5/2 mu gt over R is equal to V initial minus mu gt The r's cancel out, and then I need to combine my mu gt terms. Since the left one is a fraction, I'm going to make this be 2 over 2. So I'll add 2 halves to both sides, which is going to give me 7 halves mu gt is equal to v initial. Since I want to isolate time, I'll have time is equal to velocity initial divided by mu g, and then I'll take the reciprocal of my 7 halves, which is 2/7. So this is the equation that will give me the time where we will begin to roll without slipping. Excellent job today. Hopefully you'll be able to apply this in lots of good situations. To kind of give you a recap, you want to make sure that you can sum the forces to work through translational motion, and then sum the torques to work through rotational motion. Then you can combine them together by looking at what's going on at the center of mass.